So now let us discuss stubborn links. So what are stubborn links? These are channels that deliver any message infinitely many times, as long as the sender and the receiver are correct. So stubborn links or channels are communication abstractions that once a message is sent, it is delivered infinitely often. So that's what we call infinitely many times. This abstraction seems inefficient, but the purpose here is to guarantee that if the sender process is correct, the message is definitely delivered to a correct destination process. The purpose of this abstraction here is to show how to implement and prove the correctness of a stubborn link by composing two components together. One is a stubborn component, which in turn uses a fair loss link component. So here is the stubborn link interface. It's a module, and it has an instance SL, stubborn link. It has events, a send event to send a message to a destination. And then we have the output or indication event, which is delivering a message from a source. So the delivery will deliver message M sent by process source. We are going now to look to two properties of the stubborn link. So here is how you see this again. So a stubborn link is an abstraction, it's a component, SL, and it has a request, which is to send a message, and it delivers the message at the destination. The send, of course, will specify the destination, and the delivery will specify the source. So what are the stubborn links property? We have two properties. One is called stubborn delivery, and the other property is no creation property. So what is a stubborn delivery? It says if a correct process PI sends a message M to a correct process PJ, then PJ delivers M an infinite number of times. So if we have two processes, both are correct, the source and destination, and the source sends the message, it will be delivered infinitely many times at the destination. The other property, we have seen it before, it's called no creation, which basically say the network does not create messages out of thin air. And it says if a message M is delivered by some process, PJ, then M was previously sent by some process, PI. So this is the two properties of stubborn link. So here is an outline of an implementation of stubborn link using a fair loss link. So you use a lossy link, and then the sender stores every message in a buffer called send, and then periodically resends all messages in the buffer sent. So what we are going to do now is that we have a stubborn link with a send interface and a delivery interface, and this is going to use a fair loss link. A fair loss link. This is also a send interface, and this is a deliver interface. And again, you can see if a sender sends a message M, it will store it here in a buffer called send, and it will send it to the fair loss link, and then it will repeat sending the same messages to the fair loss link. The fair loss link itself can drop a number of messages, but eventually, because the fair loss link is fair, it has non-zero probability of delivering the message, and the message will be eventually delivered. So let us look to now to a detailed implementation of the stubborn link algorithm. So here, as I said, it uses a fair loss link. We call it FLL. And what we have here, when we get initiation event, we create a buffer which is empty, and we start a timer. Now, so this is SL, and whenever we get a send, what we do, we trigger a send at the fair loss link component. So this is the fair loss link component, fair loss link. We trigger a send here. And then we store also the message in our buffer. The message will be stored as a pair, the destination and the message. Whenever, we said before that a timeout is initiated. So whenever a timeout event occurs at the stubborn link, we resend all messages in the send buffer. So you see, for all messages in the send buffer, trigger a send. And a send means send it to the fair loss link. And then start the timer again. So we have the fair loss link here again, fair loss link. And then we get a deliver event from the fair loss link that goes to the stubborn link. So now, whenever we get this delivery event at the fair loss link, what we do, we deliver it higher up. So here we do a delivering of the message. So if this is the message M, we deliver this message. So this is the algorithm of the stubborn link. Now let us look to the correctness of the stubborn link algorithm. So what we are going to do now is we are going to see a form of a hierarchical proof. What that mean? It means to prove the properties of a component, in this case is the stubborn link, implemented in terms of other component. We are going to use the properties of those components, in this case the properties of the fair loss link, and not its implementation. So what we want to prove? We want to prove stubborn delivery. In stubborn delivery, he says if a process does not crash, it will send every message infinitely many times, and messages will be delivered infinitely many times. Okay. So how this happens? The stubborn link, when it sends message infinitely many times, it uses the fair loss property. And the fair loss property says if a message is sent by a correct process infinitely many times, it will be delivered infinitely many times to the destination process as under the assumption the destination process is correct. To stubborn delivery, assume that Pi and Pj are correct. Pi send M infinitely often, and by the fair loss property of the fair loss link, which is the fair loss delivery, M is delivered infinitely many times. Now, each fair loss delivery will cause a stubborn link delivery. Therefore, the stubborn delivery property is satisfied. Let us now look to the new creation. The new creation says that a message that is delivered, so here we have SL, and a message is delivered, it must have been sent. But the message is delivered using a fair loss link. So a fair loss link delivers the message. And we know one of the properties of the fair loss link is that if a message is delivered, it is previously sent. Therefore, the delivery at the stubborn link will also satisfy the no creation properties. Now, this is for you who have read the lecture on input-output automata. And the question is how to model stubborn links in the input-output automata formal model. If you didn't read the chapter, just skip this slide. That's not important. So stubborn link could be modeled directly in the formal model of input-output automata, and how we are going to show. If you remember, we had this notion of channels in input-output automata. And a channel had two types of action, an input action so a channel looked like this, an input-output automata. It has an input action, which is to send M from I to J, and it had an output action, which is to deliver a message from I to J. So this was a channel. And here we had process PI, and here we had process PI, and here we have process BJ. So the input action was always enabled, and it is a send from I to J. And what it does, it just stores M in buffer, which is called buffer set I to J. And what is the output action? The output action, in this case, which is called deliver M from I to J, it basically, this output action is performed given a condition, and the condition in this case was M is in a buffer set I to J. Though there is no effect of removing the message out of the buffer.